Ideal gas law, changing conditions. In this video, we will use the ideal gas law to solve for an initial or final unknown variable, pressure, volume, moles, or temperature, given the rest, and this will be under a variety of changing conditions. These are also going to start simple and get very complex. Keep in mind that what we're doing here is one topic. I'm not including a bunch of other topics that may have come from other classes. So if you start having trouble with these because of the complexity, make sure that you go review the other online videos. Now let's talk about how we can use the ideal gas law to calculate one variable as the other ones change. Let's first quickly look at an example of this sort of problem. We are going to solve it in a minute, but for now, just notice what is happening in the problem. I say, find the volume of a balloon that had the volume of 0.55 liters at sea level, where the temperature was 70 degrees Celsius, but is allowed to rise to a height of 6.5 kilometers, where the pressure is 0.40 atmospheres and the temperature is 60 degrees Celsius. So our pressure changed and our temperature changed. For this, we need to recognize that the ideal gas law can be solved for the ratio value, or the R, and that this ratio never changes. It's always the value of R. In fact, this is the very reason why we have R. So we can solve the ideal gas law for R, and since, of course, this is always true, we can solve it at both conditions. Since they are both equal to the same number, they are also both equal to each other. We can now use this equation to solve all of the problems that are generally labeled as Boyle's, Charles, or Avogadro's law problems, and it saves us from having to memorize 4 different equations. So it boils that entire section of your book down into one equation that you can solve in 3 simple steps. Let's do the example above now. We're then going to do 3 more examples where I'm going to have you work on them a bit before you watch the video, and you can watch the video as you get going if you get stuck or if you know it and need to check your work. So our first step is going to be to organize your data. It's nice to be able to write out all the information that we need in terms of final versus initial values. It's also useful to recognize that sometimes data is given that isn't needed, such as the 6.5 kilometers. This makes it easier for our brains to take in the entire paragraph by putting it into the table. From here, we can see that we have 2 sets of conditions, both involving ideal gases, and that we can use the ratio that we derived. We can then cancel out anything that doesn't change. Everything in this case is changing except for the n, so the n will cancel, and the others will stay. From here, we can fill into this equation and solve for the unknown. And these 3 basic steps will be exactly what you do for all future problems of this type. When we go to fill in our data, it's important that we notice to fill in the Kelvin temperature. Notice when I made my table, I actually added the 273 into the table to make it less likely that you'd forget. The rest of the units in this case actually don't matter. Though in this case they are in liters and atmospheres, if they were in different units, perhaps milliliters or torr, it would be okay because they would cancel. Now, why would temperature matter for units here, but volume and pressure don't? Stop and think about that a second before moving on. Okay, so let's think about how we convert volume and pressure versus how we convert temperature. When we convert pressure and volume, we're multiplying by a number. As long as the volume is the same on both sides, that multiplication factor is going to cancel on both sides. And the same thing for the pressure. So in those cases, as long as the units match, you don't need to convert. Doesn't matter what they are, but they must match. Temperature, on the other side, has an addition in the conversion factor, and that does not cancel in a ratio. And so temperature will always have to be in Kelvin. Now let's finish up this problem by rearranging and solving for volume. We put our values in straight from our table. We leave our atmospheres and liters as is. We change our temperature. From here, we can solve for V2. You are, of course, welcome to do the arrangement before you fill in or after, whatever makes you happy. Now let's do more examples. For each one, I want you to pause and work through the problem yourself until you get stuck and need help. In all of these cases, you can go through the exact pattern of organize your data, cancel things that don't change, fill in the knowns, and solve for the unknowns. Let's do another example. Argon is an inert gas that's used in light bulbs to retard the vaporization of the tungsten filament. A certain light bulb containing argon at 1.2 atmospheres and 18 degrees Celsius is heated to 85 degrees, and I want us to calculate the final pressure. This is a useful question for engineers because you would need to make sure that as you heat the light bulb, it's not going to have too much pressure for the glass and it would burst. Now, remember to try this on your own first and then come back. We need to decide what is being held constant. Volume and N are not going to change because the glass around the light bulb doesn't change and no gas comes in or out. This leaves us with just our pressure and temperatures. We now solve for P2 and fill in our numbers, being careful to convert everything into Kelvin. Remember, even though this is a ratio, the conversion factor for Kelvin is addition, and so you have to do the conversion. We put in our 1.2 atmospheres and multiply by our Kelvin final temperature, divide by our initial temperature, and we get our final answer. Now, something to always do when you do these problems is double check and make sure that your answer makes sense. We started at 1.2 atmospheres and then we heated the system. Think back to what we did last time. If we heat our system, our pressure should go up. And we can see here by the 1.48 that it does. And so it's likely that we probably did this answer correctly. This next one is very similar. Only in this case, though, the constants are going to change a bit. So here we have a bubble rising from the bottom of a lake where the temperature and pressure are given, to the water's surface where the temperature is increased and the pressure is decreased. We're going to find the volume of the bubble at the surface if initially it was 2.1 mils. Now, of course, this one is assuming that the bubble doesn't gain or lose air, but that can be assumed as part of the problem. We start from the very same part of the equation. In this case, the only one being held constant is our moles. This makes for a slightly larger equation overall. We need to solve for the final volume, or V2. I wrote this a little bit differently this time just to make it easier to trace where all the constants are. From here, we will need to very carefully fill in all of the given values. Remember that you must convert temperature into Kelvin. However, also notice my units on volume. I was given the unit in milliliters. Because we are not using R and we have a ratio, it's okay to leave this volume in milliliters. However, what it means is that when all of the other units are canceled out, we will be left with milliliters as our volume for our final volume. Remember that you are able to do this for volume and pressure only. Any unit is fine for those, but they must match each other. Now, once we have filled in these values, we can solve for our final answer, and we get a value of 14 mils. Now let's do an ideal gas problem that also has some chemical stoichiometry in it. Here I am burning octane. So octane is a gasoline, and when combusted, it produces CO2 and water. And I ask how many liters of water, measured at a particular set of conditions, is required to burn 1 gram of octane. Of course, first we must remember what combustion even is. Remember that we combust it with oxygen to form carbon dioxide and water, and that if we want to do anything with mole ratios, we're going to have to balance the equation. If you need help with how to do this, please see the old videos. Using this, we can take the 1 gram of octane and we can convert it into moles of oxygen and then use the ideal gas law. We know that we can't convert directly between grams of one thing and moles of another, and so we must first convert to moles of octane. We do this using the molecular mass of octane. From here, we use the mole ratio to convert between the moles of octane and the moles of oxygen. This gives us our final moles of oxygen. From here, it's exactly what we did much earlier in the ideal gas law videos, where we just fill in to PV equals nRT. So here we solve for volume and get nRT over P. We fill in the moles that we just determined, our ideal gas constant, our temperature converted to Kelvin, and our pressure. Notice in this case we are using the R, and so we would have to use liters and atmospheres if it wasn't given to us in those. Once we fill in all of our values, we get our final amount of liters. And so this is how much oxygen would be required if we wanted to burn 100 grams of octane completely. In review, the 2-point formula of the ideal gas law can be used to solve any of the ideal gas law problems involving changing conditions. Because it is a ratio, we can use any units for pressure and volume, but you must always use Kelvin for your units of temperature, regardless of whether you're using the 2-point or the 1-point version.